Welcome to the fifth lecture of this week. Today we will discuss about analysis of these laminates using the virtual work equation. So, this method that we are going to discuss, it is called Reed's method. So, here what we do is we express the solutions u0, v0 and w as a series like we have done before, and then we put that series in the virtual work equation or energy equation, and then we satisfy the virtual work equation, or we satisfy the condition that the total potential energy is minimum. So, to begin with, let us discuss the virtual work equation for the laminate under consideration. Again, this laminate is in the xy plane. Right now, we are doing a generic formulation. So, there can be any type of laminate or any boundary condition, and then it is under some force. Now, the force is only in z direction. So, we can call it q z, or because there is only one force, let us call it q. Now, we know that the virtual work principle says total internal virtual work is equal to total external virtual work, and internal virtual work means stress multiplied by the virtual strain. So, now here are three non-zero stress components. So, there are three components of virtual work: sigma x multiplied by delta epsilon x x, then sigma y multiplied by delta epsilon y, and then sigma s multiplied by delta epsilon s, and these things are called internal. These three quantities combined are called internal virtual work, and then we have external force multiplied by virtual displacement, and this we call external virtual work. And internal virtual work minus external virtual work is equal to 0. That means, they both are same. Now, virtual work, virtual strain we denoted by this operator delta, which is called variational operator. Now, let us put epsilon, write these strain components in terms of their components. So, epsilon x is epsilon x 0 plus z into kappa x. Similarly, epsilon y is epsilon y 0 plus z into kappa x, and similarly epsilon y is equal to epsilon y 0 plus z into kappa x. Similarly, epsilon s is epsilon s 0 plus z into kappa x. And again we know that epsilon x 0 is equal to del u 0 by del x, epsilon y 0 is equal to del v 0 by del y, and epsilon s 0 is equal to del u 0 by del y plus del v 0 by del x. And we know that kappa x is equal to minus of del 2 w by del x 2, kappa y is equal to minus of del 2 w by del y 2, and kappa s is equal to minus of twice del 2 w by del x del y. And also another thing to note is this laminate is made of total n layers. So, total this is layer 1 and this is layer n, ply 1 to ply n. So, and this sigmas are discontinuous across the plies. So, what we do is we divide this volume integral. So, here volume integral V means volume V means this entire volume of, so V denotes volume, and omega denotes, capital omega denotes the mid surface of the plate. So, this is mid surface. Now, in this particular case we can write an integral over the domain omega is equal to an integral from 0 to b 0 to a dy dx, this is same. So, because this has a length a and this has a length b. So, the along the x direction the limit is from 0 to a, and along the y direction the limit is from 0 to b, and it is a rectangular domain. So, this surface integral over the omega can also be written like this, and V is the integral over the entire volume. Now, we can break this integral volume into two integrals. So, one is integral over the surface, this mid surface, and integral over the depth, thickness. Now, if I want to integrate over the thickness these quantities, then among them this is continuous over the thickness, but sigma is discontinuous. So, we integrate piecewise over each ply and then sum it up. That is why we are summing from k to 1 to n, k is any generic lamina. So, k from 1 to n, and then we integrate over the thickness of each ply zk minus 1 to zk, and that is how all these terms are written, and this is already in the form of surface integral. And then we replace this epsilon x 0 kx by their corresponding definition in terms of the displacement components. And if we notice one thing, that if I look at this quantity, then del epsilon x 0 that is not a function of z, but sigma x varies across the thickness. So, we know from the definition that zk minus 1 zk, and then we sum it up from 1 to n, k is equal to 1 to n, and then if we integrate sigma x dz, that gives me n x, and that is what is written here. So, we have evaluated this quantity and then we are writing n x, and epsilon delta of epsilon x 0 comes as it is. Only thing is, in the place of epsilon x 0 I have put its definition in terms of the derivative of u 0. Similarly, here also sigma y, if I integrate over the thickness and sum it up, I get n y, and epsilon y 0 is replaced by del v 0 by del y. Similarly, epsilon s into delta epsilon s 0 is written here, and the definition of epsilon s 0 is here. Now, if I look at these quantities, here I have z multiplied with sigma x and then integrated, and we know that is called bending moment m x, that is what we have written here, and we have put the definition of kappa x minus del 2 w by del x 2, and then we have done the same thing here and here, and then we have q multiplied by del w as it is. So, this is the virtual work equation of this laminate in terms of the stress resultants n x n y n s and m x m y m s, and the derivatives of the displacement components. Now, for solution using Reed's method, what we do is we approximate these solutions u 0, v 0 and w. So, both all these three quantities are functions of x and y. So, we write it as a series like this, where these phi u j's are known functions of x y, that is under our control, we choose them, and each of them is multiplied with a u j, and then we sum it up. So, when j is equal to 1, this is a u 1 phi u 1, when j is equal to 2, it is a u 2 phi u 2, and so on, and we just sum it up. So, this subscript denotes that this chosen function and these unknown coefficients are for u 0. Similarly, we do the same thing for v 0 and w 0. Now, these functions the phi u j, phi v j should satisfy essential boundary conditions. Or homogeneous essential boundary conditions. in all the cases that we deal with here, we will have homogeneous essential boundary conditions, and they should satisfy that. If it can satisfy the natural boundary conditions, it is good, but it is not a requirement. So, minimum this should satisfy the essential boundary conditions. Now, if I take variation of this quantity delta, then this is composed of two quantities, one is AUJ, one is phi uj. Now, phi uj is something that we have defined, so it cannot be varied. So, something which has a value given or something which is already defined, it cannot be varied, whereas AUJ is unknown, so it can be varied. Similarly, V0 is written as this, again phi is something defined by us, so I do not vary it, that means its variation is not possible, and then we have AVJ. So, variation of AVJ. Similarly, we have delta W is equal to this, and likewise we can define the derivatives. Del U0 by del x is equal to J is equal to A to L multiplied by del phi uj by del x, and similarly we can have del U0 by del y is equal to J is equal to 1 to L A uj multiplied by del phi uj by del y, and likewise we can define the derivatives of V0 with respect to x is J is equal to 1 to L A Vj into del phi Vj del x, and del V0 by del y is equal to again summation J is equal to 1 to L A Vj del phi Vj del y, and then we define the derivatives of W. So, here we need only the second order derivatives. So, we define them. J is equal to 1 to N A Wj del Wj by del square Wj by del x square, and we have del square W by del y2 is equal to J is equal to 1 to N A Wj del square phi Wj del y2, and similarly del 2 W by del x del y is equal to J is equal to 1 to N A Wj del 2 phi j phi Wj by del x del y. So, we have assumed these quantities U0, V0 and W. We have seen their variation and we have defined their derivatives. Now, we put everything in the equation. So, if we put their definitions, here we have delta of del U0 by del x, and so before going there, just one thing, we have defined the derivatives and we have defined the variations. So, we can define the variation of the derivatives also. Del U variation of del U0 by del x is equal to J is equal to 1 to L multiplied by variation of AUJ into del UJ by del x. Del phi uj by del x. So, AUJ del phi uj by del x. Accordingly, we can define the variation of all these derivatives. So, only thing is that this quantity will be varied, but these quantities, the derivatives of phi will not be varied, because since we know phi, we know their derivatives also and they are already defined. So, with that we rewrite this expression as this. So, here we had variation of epsilon 0. So, we are writing it like this. Here we had variation of epsilon y 0, we are writing it like this. Again we had variation of epsilon y 0 here and x 0 here, and then we had epsilon. So, this is actually variation of this quantity and this quantity combinedly contribute to the variation of epsilon s 0, not epsilon y 0. So, terms has been arranged accordingly. So, this and plus this gives me variation of epsilon s 0, because epsilon s 0 is del u 0 by del y plus del v 0 by del x. So, if and we know that as per our definition we wrote, as per our approximation we wrote them as j is equal to 1 to L a u j del phi u j by del y plus j is equal to 1 to m a v j del phi v j by del x. So, if I take the variation epsilon s 0, then we get j is equal to 1 to L a u j, and we multiply that with derivative of phi u j with respect to y plus j is equal to 1 to m, and we write the variation of a v j and multiply with the derivative of phi v j with respect to x. So, these two quantities combinedly give us the variation of epsilon s 0. This comes from the variation of epsilon x 0 and this comes from the variation of epsilon y 0. Similarly, this is due to the variation of del 2 w by del x 2, and this is due to the variation of del 2 w by del y 2, and this is from the variation of del 2 w by del x del y, and this is just variation of w. Now, we can rearrange the terms and we can write it like this. J is equal to 1 to L a u j multiplied by integral n x del phi u j by del x plus n s del phi u j by del y, then integrated over the surface. So, all we are doing is we are collecting the coefficients of delta a u j and we are clubbing them together, plus j is equal to 1 to m a v j multiplied by n s into delta phi u j by del x plus delta phi v j by del x plus n y into delta phi v j by del y d omega, and then we have j is equal to 1 to m a w j multiplied by m x into delta 2 w j by del x 2 plus 2 m s into delta phi delta 2 phi w j by del x del y plus we have m y into delta 2 phi w j by del y and minus q we have. This is and then we set that equal to 0. No, this is d omega and then we set it equal to 0. Okay, so here because we have minus here, so this quantity is positive, so this is positive. So this. So finally, from this again we can put an argument that all right. So these are all deltas because of variations we are separating out. Now we can place an argument that all these variations are independent and arbitrary. So if that is so, then this quantity can always be 0 only when these terms separately are 0. So these terms separately should be 0. Similarly, separately this term should be 0 and separately this term should be 0. Because all these variations are independent and arbitrary variation. So unless these terms, I mean all these terms separately are 0, we cannot always satisfy this condition that the summation is 0. So that is what we have written here. Coefficient of delta summation, coefficient of variation of AUJ is equal to 0 and there are total L number of such quantities. So that gives me total L equations. So j going from 1 to L. Similarly, coefficient of variation of AVJ is equal to 0 and there are total m such quantities. So here we get total m equations. So j is equal to 1 to m and here the coefficient of delta AWJ is equal to 0 and there are n such quantities. So there are total n equations. So we write j is equal to 1 to n. Now with that we get all this system of equations. So there are total L plus m plus n number of equations. Now when, so let us call it system of equations 1, let us call it system of equations 2 and let us call it system of equations 3. So when Bij is B matrix is 0, then 1, 2 are uncoupled from 3. Now because B matrix is 0, then in the expression for these bending moments I will not have del u 0 by del x or the any del u 0 any u 0 or v 0 quantities. So this equation is separately for only the quantities related to W, whereas in these two equations we will have only quantities related to u 0 and v 0 and there will not be W here. So these two equations would be separated from the equation third when V matrix is 0, but 1 and 2 are coupled. And when B matrix is non-zero, then 1, 2, 3 are coupled. That means if it is a symmetric laminate, B matrix is 0, and if I am studying only the effect of transverse load, I can just deal with this system of equations. But if the matrix is asymmetric and any component of B matrix is non-zero, in that case I have to deal with all these three system of equations and solve them together. So in the next class we will see one example of this. Let us end this lecture here. Thank you.